Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors in the Geometry of Space, Section 4, Defining the Cross Product, Section 4, the Cross Product, Video 1, Defining the Cross Product. Now, even though I'm making a series of videos for Calculus 3 in general, this specific video is a continuation of the topic that we started in class in the course that I'm currently teaching in the fall of 2023. The date of the class was Wednesday, September the 6th, 2023. So unlike most videos, this already has some of the stuff figured out. In other words, we're going to summarize what we talked about in class. Well, at the time of this recording, what we talked about in class yesterday. We started with the following. We're defining the cross product of U and V, vectors U and V, denoted U cross V. That's how you would say that. The cross product produces a vector that is orthogonal to both U and V. So we start with any two vectors, and we want to find a third vector that is basically perpendicular to the two given vectors. Now, the cross product is defined only in R3. Now, as I mentioned in class yesterday, you can kind of talk about it in R2, two-dimensional vectors, by embedding them in R3 by thinking of them as living in the XY plane, and then the orthogonal vector would go parallel to the Z-axis. So we didn't talk about the right-hand rule yesterday. I'll find an opportunity to bring it up in a future video in this series. So unlike most calculus classes, I didn't just give you the formula for the cross product. We're going to find the formula for the cross product so we can kind of see where it came from. So we're going to start by letting U and V be written in component form. Vector U is 1, 2, 3. Vector U is U1, U2, U3, and vector V is V1, V2, V3. I think I can do some highlighting here to Okay, it's not letting me highlight. Maybe I can do it this way. All right, so there's vector, there's U, and there's V. All right, and we want to find a vector called U cross V, but for the sake of simplicity, we're going to just name it W for now, and its components W1, W2, and W3, such that U is orthogonal to W, and also such that V is orthogonal to W. Now, what we know about being orthogonal, perpendicular, if you will, is that two vectors are orthogonal if and only if their dot product is 0. Now, of course, if one of those vectors is the 0 vector, then it's somewhat trivial. So for the sake of moving forward, we're going to assume that we do not have the 0 vector. We're just looking at non-zero vectors in R3. All right, so we're going to capitalize on the fact that the dot products of U and W and V and W both have to equal 0. And using the component definition of dot product, we get the following equations. Just a reminder, the component definition of dot product meant that we took the component forms of the vectors and we took the sum of the products of the corresponding coordinates. So U1 times W1 plus U2 times W2 plus U3 times W3 is equal to 0, which is what we see right here. And if we did the same thing for V and W, then it would be V1 W1 plus V2 W2 plus V3 W3 is equal to 0. All right, now we have a slight problem here. We're trying to find three components of the cross product, which are currently labeled W1, W2, and W3. But we only have two equations, and we have three unknowns. We're assuming we know the U's and the V's. We don't have enough equations to uniquely solve for W1, W2, and W3. And this sort of makes sense because if you took two vectors and you wanted to find a third one that was orthogonal to them, so let's take these two non-perpendicular vectors and make this one perpendicular to it, then this vector could be any magnitude as long as it had the correct direction. And it could go in the opposite direction and have basically a negative scalar multiple of the one that was up here. So there are an infinite number of vectors that are mutually orthogonal to U and V. We're going to try to find a formula that gives us the easiest looking version. And I will warn you now, the formula is not as easy as the dot product formula, but it is manageable. All right, as I mentioned, this is a system of two equations and three unknowns. In linear algebra, this is called an underdetermined system, meaning that we don't have enough equations to find a unique solution. In general, from a linear algebra perspective, when there are more equations than variables, and this should say than right here, not that, there are either no solutions or an infinite number of solutions. To obtain a unique solution, we would need at least three variables. but I digress. This is not a linear algebra course. Now, in such a case where we have more variables than equations, we can assign at least one of the variables to be free in the sense that it can obtain any value. Then we solve for the remaining variables in terms of the free variable or variables. In general, the number of free variables is the difference between the number of equations and the number of variables. So in this case, there's 3 equations, 2 variables. 3 minus 2 is 1. We're going to have 1 free variable. I say in general because for those who know more linear algebra than this course covers, it could be possible that 2 or more of the equations we have are linearly dependent, in which case we would actually have an extra free variable. But let's not go down that path any further. All right, so between W1, W2, and W3, we can choose one of them to be free. Let's just let W1 be a free variable. So we're going to solve for W2 and W3 in terms of W1, U1, U2, U3, V1, V2, and V3. Remember, we know all the U's and V's, and we're assuming W1 can be anything. So let's go back to the system of equations. The first dot product is equal to 0. The second dot product is equal to 0. And we're going to set up an elimination for W3. In other words, I want these to end up canceling each other. The standard way to do that is to multiply each equation by the coefficient of the variable in the other equation and making sure they end up being opposite. So that's a fancy way of saying I'm going to multiply the top equation by V3 and the bottom equation by U3. That'll give the same products. But we need to make sure that they're opposite, so one of them needs to be negative. We're going to multiply the top equation by V3 and the bottom equation by negative U3. If we take this top equation here, which I'm about to highlight, and if we multiply it across by V3, we get this equation. And if we take the bottom equation and multiply through it by negative U3, we're going to get here. Everybody picks up a U3 and everybody becomes negative. I do plan on saving this PDF that I'm highlighting to make available for anybody who wants it. So I want to make sure the color coding is consistent. Now, by our choice of multipliers, we have now set up opposite terms on the W3. So when we add these equations, they will cancel. Adding the equations together will give us this new equation, which I'm going to highlight in green. It's basically this guy minus this guy plus this guy minus this guy, because the other stuff cancels. All right, I'm not sure if I can get rid of just the green. That's what I was afraid of. Give me 1 second to reset these. Unfortunately, and I'm just using Microsoft Edge to view and edit this PDF. Control-Z does not just undo things. All right, so when we add those equations together, we get all the expressions that you see there. And you'll notice that the 2 terms on the left, these 2 terms here, have W1 as a common factor, and the 2 terms on the right have W2 as a common factor. So we're going to factor the W's out of each half of this to get U1 V3 minus U3 V1 as the coefficient of W1, plus U2 minus V3 minus U2 V3 minus U3 V2 as the coefficient of W2 equal to 0. And now we can solve this for W2. I'm not going to go through all the algebra, but we would move this guy over, so it'll pick up a negative sign, and then we would divide by the coefficient of W2. And the net result of doing that is this. W2 is equal to this fraction times W1. Now, what if the denominator is equal to 0? Well, for now, we're going to assume it's not. That is discussed a little bit more in depth, especially in a linear algebra class. But to solve for W3, because realize right now what we have is we have W2 in terms of the values that we know, the U's and the V's, and the free variable W1. And we're going to do the same thing for W3. Now, I was debating on one of 2 ways. In class, what I'd started and we're going to finish is we take the expression for W2 and substitute it into one of the original equations. In this case, if you take the equation in yellow, let's go up higher. If you take this equation in yellow, remove the W2 and replace it with what's in this box, you end up getting the equation that you're currently seeing. It's a little bit messy, but it is what it is. But notice that from an algebraic perspective, this is an equation that has W3 in terms of stuff we already know, all the U's and the V's, and the free variable W1. So I can solve this for W3. It'll be W3 equals a function of W1. And this is where we're going to pick up the instructional video. All right. So now we want to solve this for W3. So how are we going to do that? Well, all we have to do is move all this over. So each of the two terms will exchange signs. I say two terms because this is a term and this whole mess here is a term meaning a product. And so those will change signs, and then afterwards we'll divide by U3, or we can multiply by the reciprocal 1 over U3. All right, so let's see how cleanly I can write this, because now I got to break out my stylus, and my stylus hasn't been writing too well lately. All right, so we're going to start by leaving the U3, W3 on the left. I can already tell I'm going to have trouble with this stylus because my U doesn't look anything like a U. All right, let's try this. Let's try drawing it with my finger. U3, W3. And if we move this term from the left to the right, it will become negative. So minus U1, W1. And if we move this whole term to the right, it'll change signs, but I'm going to capitalize on the fact that it currently has a negative sign on it. So when I move that entire expression over, it will lose that negative sign, and we'll end up with plus U2 times a fraction that has U1 V3 minus U3 V1 over U2 V3 minus U3 V2. And that's what we have, because the right side of the equation was originally 0, and we just moved a couple of terms over there. All right, let's erase some of these arrows. All right, before we solve for W3, I think it would be in our best interest to try to simplify this expression on the right. And being a fraction, I want to get a common denominator. The common denominator will be U2 V3 minus U3 V2. And in order to get that common denominator, the part that's not a fraction needs to be multiplied on the top and bottom by the common denominator. That will put that circle term multiplied by the denominator. And so we will pick up negative U1 W1 times the denominator, U2 V3 minus U3 V2, and then plus the numerator of the second fraction, which already has the common denominator, except the second fraction has this U2 in front of it, and it's going to go up here and it's going to distribute across the two terms in the numerator. We'll do that in a moment. For now, let's just put everything on the top. So we'll have plus U2 times U1 V3 minus U3 V1. All right, let's get this simplified. Here's our denominator, U2 V3 minus U3 V2. And on the numerator, we just have to do some distributions. Just that was supposed to be a highlight. Let's try that again. Distribute here and there, and also over here. So we're going to do the distributions over there. The first distribution ends up being negative U1, U2, V3, W1. And the second distribution ends up being plus U1, let's put everything in numerical order, V2, U3, W1. And then the second half of the distribution will become, I feel like we're missing something. Hold on. Aha! I lost something. I lost this W1 here. I lost this W1 here. Why is it not highlighting? Hold on. Something goofy's happening. I missed this W1 here when I move the fraction to the right. So luckily we can rectify that fairly easily. We just have to sneak the W1 here, and we'll sneak it on the right side of this parentheses. And now we'll distribute not only the U2s, but the W's from the right. So we'll distribute this guy across here as well. So we're hitting it from both sides. All right, so that means that the first term on the distributions from both sides will be in numerical order, U1, U2, V3, and then W1. I'm saving the W last because it's the variable we're solving for. And the second half will be minus V1, U2, U3, W1. All right, so this is becoming a colossal mess unless we can find something that we can take advantage of. And I see something that we can take advantage of. What is that something? This term up front and the third term are opposites, and therefore they cancel. So those are going to disappear. Now let's scrutinize the remaining terms. Let's scrutinize the U1, V2, U3, W1, and the minus V1, U2, U3, W1. Now, what do they have in common? Well, they clearly have a W1 in common, but they also have a U3 in common. So I am going to factor out what they have in common. All right, our denominator is U2 V3 minus U3 V2. Our numerator pieces, move my head up here. Our numerator pieces, after we take out what's in common, which is the W1 and the U3, are U1 V2 minus V1 U2. And then we are factoring out both the U3 and the W1. Now, keep in mind that all this was equal to U3, W3. So let's bring the U3, W3 down. And assuming U3 is not equal to 0, we can divide both sides by it. And we finally end up getting W3 is equal to U1, V2 minus V1, U2 over U2, V3. And I'm going to make a very subtle change here for the sake of consistency. This term down here, I'm going to write in the reverse order because I'm trying to write the lower subscripts first. So we're going to write it as V2, U3, W1. All right, so what it means as I zoom out some is we now have expressions for W2 as a function of the U's and V's, which we're assuming we knew what those two original vectors were, and the free variable W1. And we have W3 as a function or as an expression in terms of the U's and the V's and the free variable W1. So now we can string together this W2, this W3, and W1 into some component representation of W. All right. The first component was originally W1, and it was our free variable, so we're going to leave it there. Our second component was W2, which is the expression that you see here. I'm going to do two things as I recopy it. Number one, which I did previously, I'm going to reverse the order of this product just so that the subscripts are in a numerical order, in increasing order. And I think I'm going to take this minus and distribute it across here, which will turn the subtraction problem around. So the top's going to start with U3 V1, and the bottom's going to start with U2 V3. The top's going to start with, I forgot what I said. The top's going to start with U3 V1. And I don't have to scroll back up to look because I know from experience that these subtraction problems basically just switch subscripts. U3 V1 and then U1 V3. Again, I'm kind of violating the subscripts being in order for now, but we'll fix that as necessary. And then the denominator was, and again, I'm going to reverse the order here, U2 V3 minus V2 U3. U2 V3 minus V2 U3. In fact, I think I'm going to go ahead and reverse the order. Well, do I want to keep numerical order or do I want to keep alphabetical order? Let's keep alphabetical order. So down here is I know, why are you changing? Because I'm trying to remain consistent. So as we push through this, any product I'm going to put in alphabetical order, U first, V second. Now be careful. That was not W2. That was the coefficient of W1 in the expression for W2. So this has a W1 attached to it. And we do the same thing for W3, which is the expression right here. And again, as I transcribe this from here to here, I am going to rewrite the products with the letters in alphabetical order. So the numerator becomes, or is U1 V2 minus U2 V1. I thought about it, I knew alphabetical order was better all along. The denominator is U2 V3 minus U3 V2. And all of this is multiplied by W1. Kind of ran out of room there, but I think you see what I was going for. Okay, so is this the formula for the cross product? Well, no, this is a formula that will give a mutually orthogonal vector to both U and V. But I'd like a little better looking answer. So what can we do? Well, the answer is if we multiply a vector by a non-zero scalar, we get a vector in the same direction, parallel, if you will. So if we have a vector and we make it twice as long, it doesn't change the fact that it was orthogonal to something. So like if this was orthogonal to U and V, then so is this. So we can multiply by any non-zero scalar to preserve orthogonality and give us a slightly better expression. Well, what would make this expression look better? Well, number one, if it had no fractions. So I'm going to choose to multiply by a scalar that will eliminate the two denominators. And if you've been looking closely, you'll have observed that our two denominators are already the same. How nice for us. So whatever is going to take out one denominator will take out both of them. And notice that all three components have a W1 as a factor. That was kind of by our choice. We said W1 will be free, and let's solve for the other variables in terms of W1. So if I want to simplify this quote-unquote formula for the quote-unquote cross product, I'd like to take advantage of both the fact that the denominators match and they all have W1s. So I'm going to multiply. I'm going to multiply by a scalar of, and let's see, I guess I'm gonna have to draw this. To get rid of the fractions, I need to multiply by a scalar multiple of U2 V3 minus U3 V2. And to get rid of the W1, assuming it's not zero, we're going to multiply by, or we're going to put W1 in the denominator. So this will cancel all the W1s, cancel all the fractions, and in the first component, it's going to put this. So that's going to go in the first component. The second and third components will lose their denominators. Everybody will lose their W1s, and our formula for this mutually orthogonal vector becomes the following. The first component loses the W1 and picks up U2 minus V3. I'm sorry, U2 times V3 minus U3 times V2. The second component loses its W1 and its denominator and becomes U3 V1 minus U1 V3. And you'll notice there's some symmetry in each of these subtraction problems that the subscripts just switch between U and V. And then the third component is going to lose its W1, lose its denominator, and become U1 V1 minus, no. U1 V2, excuse me. minus U2 V1. So is this the definition of cross product? Yes, it is. So U cross V is this. Now, this formula looks like a pain to memorize. I'm going to make one comment to wrap up this video. In the next video, I'm going to show you some gimmicks for memorizing it and evaluating it. But you'll notice some consistencies and similarities amongst the components. For example, the first component has no 1 subscripts. The second component has no 2 subscripts. And the third component has no 3 subscripts. So the ordinal number for the position, first, second, or third, does not show up as a subscript in the calculation of that component. First component doesn't have any 1 subscripts. Second component doesn't have any 2s. Third component doesn't have any 3s. Is there anything else you can notice? Well, yeah. The first component, if I can get this to work, starts with a subscript of 2. The second component starts with a subscript of 3. And the third component starts with a subscript of 1. Specifically U2, U3, and U1. So you can think of starting each formula as starting with U subscript the next position, with the convention that if we're in the third spot and we go to the next one, we wrap back around to the first. And you'll notice that within each product, the subscripts just trade places. So it is possible to memorize this formula using the following gimmick. U cross V. All right. Each component starts with the first vector component, so it starts with a U, but the subscript is the next position. So for position 1, I would start with U2. For position 2, I would start with U3. And for position 3, I would wrap around and start with position 1, U1. Secondly, each of the products is U and V. Thirdly, each position is missing the subscript that matches that position number. So the first component has no subscripts of 1. So the V has a subscript of 3. And it is worth mentioning that within each product, U times V, the subscripts are different. So the second component has no 2s as subscripts. So it's U3 times V1. And the third component has no 3s as subscripts. So it's U1 V3. They're all subtraction problems. And for each one, the second part of the subtraction problem, the subtrahend, I believe. I always get subtrahend and minuend backwards. The second half of the subtraction problem, you simply switch the order of the subscripts as the first half. So for example, in the first component, instead of U2 V3, it's U3 V2. In the second component, instead of U3 V1, it's U1 V3. And in the third component, instead of U1 V3, excuse me, that's not right. Third component should not have a subscript of 3. Each component here is missing the subscript that matches its position. Subscript should not be 3, it should have been 2. Minus the same order except reverse the subscripts, U2 minus V1. That should be the definition that was right up here, or the result. Just checking it real quick. Ta-da. All right, in the next video, because this one was already too long, we are going to calculate the cross product. And I think we'll just do some calculations, and then we'll verify that the result is indeed orthogonal to the original 2 vectors. And then in the third video, we'll look at different ways to remember the cross product formula.